Namaskar. Today we have another speaker, Dr. T. Hemalatha. Dr. T. Hemalatha, she did her postgraduate from NIT Tiruchirappalli, got her PhD from IISc Bangalore, currently working as a principal scientist in CSIR Structural Engineering Division, Chennai. She was awarded a CSIR Raman Research Fellowship and visited Georgia Institute of Technology, USA. Her research interests include supplementary cementitious material, high volume fly ash concrete, mechanics of materials, self-compacting concrete, microstructural characterization, sustainable building material, nano engineering concrete, fracture and fatigue of concrete, textile reinforcement concrete, electrically conductive concrete, recycle concrete aggregate. She was involved in the transfer of technology of reinforced concrete product to various industry. She has delivered invited lectures in many institutes, including IITs. With this introduction, now I request Dr. Hemalatha to deliver a topic on circular economy in built environmental. Now it's over to you, ma'am. Is it audible?
Yes, sir.
Yeah, ma'am, can you?
Yeah, I'm sharing my slide.
Ma'am,
Yeah, I'm
ma'am,
sharing.
before after sharing, you please disable the Android mode in the top of that sharing. We are from technical team of NITTR Kolkata.
Yeah, 1 minute.
Yes, ma'am.
So now, yeah, share. I'm clicking it. Is my screen visible?
Yes, ma'am.
It is visible.
Visible?
Yes, yes.
Yes, ma'am.
1 minute. Then 1 minute. It's not visible to me. I'm stopping my video. Just a minute. I'll take the help of my daughter and sort it out.
Okay, madam.
Just a minute. Sharing is not coming full screen. Yeah. Am I audible?
Yes, ma'am.
Yes, ma'am. Yes,
Yes,
ma'am.
Okay. Thank you so much for the introduction. First, I would like to congratulate Professor Naveen for choosing such a nice topic, which is need of the day for this particular workshop. And I would like to thank Professor Naveen for giving me this opportunity. So today the topic is circular economy in built environment. as introduced by an ATTR staff or student. I am a structural engineer and I am working on my research interests on development of sustainable building materials. So first, let us talk about this. What is circular economy? Because this program is attended by people from different disciplines. I thought I'll not go in detail into what we are doing structurally and talk more about the results. Instead, at SERC, CSIR, SERC, what are the research work it is going on, which is contributing towards the circular economy. So this is how I designed my presentation today. So before going into the presentation, I just want to put few questions to the audience, like why the circular economy, and I don't know whether everybody is familiar with this term circular economy. So first, I'll just introduce what is the circular economy in general, and then let us pass on to the circular economy in built environment. So first, I would like to put few questions to the audience. See, what we are today, what are the luxury thing what we are enjoying today? What we are missing our parents and grandparents, those who enjoyed in their early days. Like I just want to mean that we are having a sophisticated house, luxury car, everything. But whether we are having a clean air to breathe and clean water to take, to drink and take bath, and space, open space for playing, everything. What our ancestors or grandparents or parents enjoyed in those days. So those whether what we are going to give it to our kids and grandkids. So that's sustainability. So the circular economy is all about what we are going to give something to our future generation. So as I mentioned here in the title, balancing our needs with earth limits, because we are so greedy, we are cutting the greeneries and we are moving towards making the concrete jungle. So by balancing our needs with earth limits, in the coming slides, we will see how we are exploiting and we are ruining the environment. So here I have given 2 points. One is balancing our needs with earth limits. Another one is finding ways to share and preserve resources collectively. Moving on to the slides. Here I have made the outline like circular economy in general, and United Nations have developed some sustainable development goals. So whatever research activities what we are doing, it is moving towards achieving those sustainability goals. And circular economy in construction. And I would like to show some glimpses of work which we are carrying out CSIR-SERC towards achieving circular economy. So coming to the definition of circular economy, it is only the word is new. The circular economy, the term is new, but it is nothing but what we are doing for so many years together, like reusing, recycling. So the very concept of circular economy is, it is eliminating the waste. One is to eliminate the waste, reduce the waste. And the next point is how we can extend the life or keeping the resources alive. So these two, if we are able to make, then we can moving towards the circular economy. So in the difference between linear economy and circular economy is, in linear economy, we'll make and we'll use it and we will dispose it. So it leads to, it generate huge waste generation. It results in the generation of huge amount of waste. When it comes to circular economy, it is just like by all means, we want to reduce the waste and we want to extend the life of the structure or material. That is the difference between linear economy and circular economy. Now here, as I mentioned, it is circular economy. The term is only new. It is not a new concept. What we used to do, whatever we have, like a dress, chapel, whatever utensils, whatever it is, if it goes bad, then we used to try to repair it and use it. So, and like plastics and all, it is recycled and made into a different material. So it is like there is no newness in the concept, but the term is concept. But the circular economy is little beyond the recycling. So that is what I just want to show it here. In linear economy, it is take, make, use, waste. It goes as a waste. Whereas in recycling economy, take, make, use, and certain stage it can be recycled, and the life of the material or structure is extended to some extent. Whereas in circular economy, so it is like there are so many concepts in which the material can be in use for a long time. So if I go to the next slide, we can see what I mean to say from the circular economy. Whereas in a recycling economy, it is only the recycling. Whereas in circular economy, the material or structure can be in use by different means, like when materials are recovered after the end of life products, and it can be made into another material in recycling. Whereas another term, it is remanufacturing. So disassembling at the component level, then it can be assembled and it become a new product. So this is also another concept. It is, see, different concepts are in use now, and another is redesigning and reusing and maintenance. So refurbishment, remanufacturing. So these are some of the terms. There is a very narrow difference between each and everything, and repair everything, it comes under the circular economy. So by the entire concept is instead of just throwing out, whether it can be recycled or reused or repaired, the life of the material or structure can be extended. This is the main idea of the circular economy. So if we see in modern days, if you ask your parents or grandparents, if something is going bad, like TV, shoes, dress, any electronic gadgets, anything, earlier we used to repair and use it. But nowadays what we are doing, instead of repairing, we are going for a new purchase. The reason why it is happening, because there are two reasons. One is nowadays the volume of manufacturing is high and affordable. So the cost is affordable, and nowadays the repair is costly. The repair is costly in the sense it is so because the people are moving towards buying a new item rather than repairing and use it. The skilled labors for repairing the product is very less. So it is like vice versa. We are not encouraging the repair, so the skills for providing repair is less, and because the repair skilled repair people are not available, we are not going for the repair. So it is vice versa. So what happens? This is not only we are spending more money for buying a purchase of new material. If we consciously see, we are generating more and more waste, and ours is a most populated country, and we don't afford to have space just for dumping the waste. So the circular economy concept is very much useful and very much we have to follow in developing country like India to convert the waste as a resource. So if you see any industry, they are having two major problems. One is due to emission, another is due to the waste generation. So if they are able to reduce the emission, and if the waste generated in the industry is converted as a resource, so most of the problem will be solved. So now I have to, this is a butterfly diagram. This is concept. This is the diagram which can explain the circular economy concept in a well manner. So with this, I'll conclude the general topic of circular economy. Then we move on to why we need the circular economy in built environment. So I just want to take few minutes to explain this butterfly diagram. So if you see this butterfly diagram, left-hand side is biological material and the right-hand side is technical material. So if you see that left-hand side of the butterfly, so the first inner loop, nowadays we are having biological material that can be converted into a useful products. Like banana stem can be made as a fiber and can be made as a dress materials, and the plates, organic plates are made of some bio materials. So the organic material or biomaterials which are able to made as a product that comes and in the inner loop. So it goes to the part manufacturer, it becomes a product, it goes to the service provider. If you see the material which cannot be used, so if you see the left hand side is a consumed product and the right hand side is the product which can be reused. So the biological product, which cannot be made it or cyclable, which is decomposed and go into the soil, biodegradable material in the soil, then it comes in a outer loop. So this is for the left hand side. So this explains how the circular economy is applied for the biological material. When we see the right hand side of the butterfly diagram, this is what I told you. There are so many concepts or different methodology we can apply for adapting the circular economy. Like in the first, if you see the first thing, here, this can be the item can be repaired and again it can be put into the loop. Then item can be reused. Thanks to nowadays, thanks to OLX quicker kind of platform, wherein the material which is not useful for somebody can be useful for somebody else. That they are giving the platform to purchase at a lower cost, and also they are helping the item which is in a which service life can be extended. So by that way, we are contributing for the waste minimization. Then when it comes to the refurbish and remanufacture, the certain broken parts can be removed and again it is repaired, and this can be come out as a new product. So nowadays there are so many shops it is available wherein we will get the refurbished or remanufactured items. Especially in mobile shops, we can get now refurbished and remanufactured products. Like that, many shops are available wherein people, those who cannot afford for a new item, they can buy it from a refurbished or remanufactured shop with a lesser cost. Then recycle is the concept. We all know that there's plastics, scrap steels can be recycled and again it can be made into another form of plastic and recycling. So This is for left hand side is for biodegradable material and non-biodegradable material. So the concept is different for these two different materials, but for the non-biodegradable, there are different methodologies to have the material in use for a longer period. Now let us move on to our. This is just to show that United Nations, it is insisting upon going towards the sustainable development by implementing certain goals. All are notably, they are for health and well-being, advancing net zero and circular economy. So why circular economy is very important in built environment? Because this building and the activities of buildings, it contributes towards a significant share of carbon emissions, energy and material consumption. Building contribute to approximately 35% of global energy consumption and 39% of carbon emissions. That is why, as a structural engineer, I have to say that we are the more devastating the environment. Because this construction industry, or as a whole, or concrete industry in particular, it is contributing for the waste generation as well as the higher amount of emissions. So concrete is the second largest material consumed in the world next to water. So if you see the ingredients, why I am saying that concrete industry is contributing more towards the environmental degradation, because the ingredients, if we see the ingredients of concrete, cement, fine aggregate, coarse aggregate, water and steel. So this is the conventional ingredients which is required for making of the concrete. And nowadays we have different special types of concrete wherein we'll add some other new materials also for getting some required functions. So first, if I take the cement, almost for manufacturing 1 ton of cement, it produces around 1 ton of carbon dioxide. So, and India is the second largest producer of cement. So we can imagine how much carbon dioxide emission it is created only by the cement industry. Then coming to the fine aggregate, the conventional fine aggregate is river sand. Nowadays, we are having alternate fine aggregates like manufactured sand, and now we are researching for, because now we are running out of river sand and we are not at all having river sand. So I'll show slides how sand mining has devastated or degraded the environment. Similarly, coarse aggregate, it is quarried from the mountains. So each and every ingredient of the concrete, it is contributing for the environmental degradation. So when we are giving attention to all these ingredients, then now we have started using the Portland Pozzolana cement, slag cement, all those things in terms of moving towards the circular economy. So this is to show that industrialization, it is giving CO2 emission and also generating waste. So these are the two major problems of the industry. And if you take for built environment, if we take the steel making produces around 6% of CO2 emission, whereas cement manufacturing 8%. So India is the fourth largest emitter of CO2 and second largest producer of cement and steel. So when we are able to find alternate for the ordinary Portland cement, then we can reduce the carbon dioxide emission coming out from the cement industry. So now, as I having said that this concrete is made up of fine aggregate, coarse aggregate, have you ever thought that what is the origin of this raw materials which is going into the construction? So it's all requires mining, logging, and other processes. So why we have to worry about the built environment is because the construction industry is responsible for over 30% of extraction of raw materials and at least 25% of the waste in the world. And when we see the building reach the end of life period, only 40% of the material is recycled and reused. So if we are aware of what are the problems it is coming from the construction industry or concrete industry, and what are the problems which can be altered, which is in our hand to reduce this kind of degradation to the environment. So this is just to show that because fine aggregate in a concrete, around 70 to 80% of the volume is occupied by the aggregate, both fine and coarse aggregate together, and both fine and coarse aggregate are from the natural resources. So this is just to show that how we are degrading the environment or natural resources by mining sand. So this is the satellite image of China Poyang Lake and Yangtze River. The first image is from 1995 and second image is 2013. So if you see the course of the river and the width of the river, how it has been changed in from 1995 to 2013. So what are the effects which we are facing due to the sand mining? This is change of course of the river. It threatens water security. It lowers the groundwater capacity, raising water cost, reduced biodiversity, saline water intrusion, so many things. So as I mentioned, like India is the second largest producer of cement and steel. The sand and gravel are the second most used natural resources just after water. So when we are able to give some alternative materials for the river sand, then we can reduce the impact due to this construction materials. Similarly, it is the quarrying of stone. This is the image of Aravalli Hills range. So they have mentioned just because of this, whatever climatic change, what we are facing now, we are floods in many places, landslides, all those things, and extreme hot and extreme cold weather condition, everything because of this devastation of the natural resources. So here they have given an example that this weathering pattern has been changed, like from the day of onset of monsoon to the day of its withdrawal. Earlier it was 101 days in 1973, wherein it became 25 days in 2009. Similarly, the total number of rainy days has declined from 60 to 80 days per year to 18 to 30 days. This is because we all know that we have studied in geography that how important the location of mountain is to get a rainfall. So when we are quarrying for aggregates, exploiting the mountains, then we are ending up with extreme hot weather and cold conditions. So with this, I'll just move on to the work what we are doing towards the circular economy. Here, I have just taken an example like building construction. After its service life, once the life is ended, then we'll go for demolition, and demolition waste we are just landfilling. So this is what happening in linear economy. Whereas what we are doing in circular economy, once after construction, one service life or end of the life, then the building is demolished and it has been converted as a recycled material. So now we are having but the number of units are very less. We have to go far away to do the recycling of materials or bringing the acceptance of recycling materials in the place of conventional fine or coarse aggregates. So this is just to mention that we have to move towards developing the green concrete as an alternative to conventional concrete to reduce the CO2 emission and to leave the mines depleted. And this is one data like this Netherlands. Yeah. So this is data which is which shows that Netherlands has 120 C&D waste recycling facilities for the population of 1.72 crores. And we in India, we have only 10 such facilities for a population over 134 crores. So this setting up of recycling units are slowly picking up because there is no takers for the recycled aggregates. Now, whatever it is produced, this is not picking up. But considering the depletion of natural resources, we are running out of, there is a huge demand. We can expect a huge demand for coarse and fine aggregate in future. So in that case, we are left out with the options like recycled aggregates. So we have started some work recently. We have a project on recycled aggregate. And this slide shows that what are the different areas we are working towards the circular economy. Like one is in the development of alternative aggregates. We have tried copper slag, fly ash aggregates, recycled aggregates as an alternative for fine and coarse aggregate. Similarly, alternative binders, high volume fly ash, geopolymer, GGBS, that ground granulated blast furnace slag, etc. Then coming to the second item, that is reducing the production of waste. It is by thin section structures and reuse structures. ACRC is working on this area also. And coming to the third one, it is maximizing the value of recovered materials throughout all stages of the program. So prefab construction, and we are working on durability, repair and rehabilitation to extend the life of the structure. And as I mentioned, when we are using industrial byproducts as an alternative for conventional material, we have developed different types of concretes, special concretes, especially by using one or more material as a industrial byproducts. Like these are some of the types of concrete we are working on, like recycled aggregate concrete. So from the construction and demolition waste, we are researching on both recycled fine aggregate and coarse aggregate, and fly ash. So in India, we have around 145 thermal power stations. So you can imagine the quantum of fly ash generated in each thermal power station. Now, at least after so much of effort, the utilization of fly ash has been got good acceptance by the cement industry because of the benefits. I have few slides to show what are the research work carried out by using the fly ash. And other types of concrete like pervious concrete, self-compacting concrete, electrically conductive concrete, textile reinforced concrete, steel slag aggregate concrete. So each and every type of we tried to use at least one industrial byproducts as an ingredient for developing a special concretes. Like this is the different types of industrial byproducts which we have used, like fly ash, which is from a thermal power station, GGBS from steel industry, steel slag from steel industry, lime sludge from a paper industry. silica fume from ferrosilicon, rices, cash, agriculture sector, eggshell powder from food industry, recycled concrete from construction industry. So these are some of the industrial byproducts we are using for developing new types of concretes. First, let us see some work which we have carried out on recycled aggregate. And this is the data where we are only using 1% of C&D waste produced. Everything goes as a landfill. And India needs to add 700 to 900 million square meters of commercial residential space every year till 2030. So we can imagine that how much of C&D waste we are going to produce. But we don't have the infrastructure, or as I mentioned, we don't have the processing facilities for making the recycled aggregates. So these are some of the reasons they have listed out why this is not happening, like lack of documentation, limited awareness, policy gaps, unauthorized practices. So here I have shown how this recycled aggregate looks like and how we are making the recycled aggregate. So this is from an old concrete. It is crushed and we removed the coarse aggregate from this old concrete. So the problem with the recycled aggregate is when we are crushing and removing, it is very difficult to remove the mortar which is adhered to the aggregate. So this creates a interfacial transition zone. So when we are using recycled aggregate, it may be having two interfacial transition zone, one between the aggregate and the old mortar, and when this aggregate is used in the new mortar, the transition zone between the already othered mortar and the new mortar. So generally the interfacial transition zone is the weakest zone in the concrete. It creates a problem like cracking. So when we use recycled aggregate with the two interfacial transition zone, it further weakens the concrete. So this is the disadvantage of using the recycled aggregate. So the research is going on to bring the aggregate without othered mortar. And this is another problem. This is from the processing unit. They have certain technologies to remove the othered mortar, but what happens, the segregation is not proper. So it has a mix of everything. Like it has concrete, aggregate, gravel, brick pieces, tile pieces, everything together. So here the segregation is a big problem. So when it comes to the physical properties which is affecting the strength of the concrete, there is a variation in the normal aggregate, conventionally it is used, and the recycled aggregate. So these are some of the challenges we have to sort it out by doing research, and definitely this can be come out as a alternative for, bring it out as a alternative for conventional aggregate. This is the recycled fine aggregate. Again, in the processing unit, after crushing and it is passed through so many stages, we can get the processed recycled fine aggregate. It looks like this. Here also, it is a combination of so many things, like it contains ceramic pieces, mortar pieces, brick pieces, everything. And because of this combination of all these things, the physical properties and chemical properties gets altered. And when it is compared with, this is the morphology of river sand, M sand, and recycled fine aggregate. M sand is angular in nature. Just by seeing under the scanning electron microscopy, we can come to know the particle morphology, because this shape, size of the material, it affects the mix composition and in turn the compressive strength and other mechanical and durability properties. So just we have seen with this after crushing construction demolition waste, whether this can be how this particle size as well as the shape of the material varies. And also, see, whenever we want to use some new material in the place of conventional material, we have to see for the same composition of the material how the new material behaves and how the conventional material behaves. So this is just to show that this for A and C are with recycled fine aggregate, and B and D are with M sand. But because nowadays we are not at all having river sand, so it is logical to compare the M sand, whatever we want to use, with the M sand, which is nowadays used generally in all construction projects. So here we have used for the same composition of the material. When we use recycled fine aggregate, we can see that the flow is affected because of, as I mentioned in the earlier slide, it is having the combination of different type of materials. The water absorption and other properties differs, and it is reflected in the flow as well as the strength properties. So this is for recycled fine aggregate. Then when it comes to the strength result, here we have used both river sand as well as the M sand to see how, when we are making changes in the replacement level, so up to what extent, because when we are using some new materials, we should know up to what replacement we can go, whether we can go for 100% replacement or partial replacement without affecting the strength as well as durability properties. So we have seen with how whether recycled fine aggregate can be used instead of M sand or river sand. So from the strength result, we have observed that there is no problem with the strength, even though it is having a problem of water absorption, but it is within the range of what code specifies. So that is reflected in the strength. And the another observation what we have got here is it is not affecting the 28-day strength, but it is affecting the early age strength. So that has to be, if we want to use it for such kind of applications, then we have to give attention, or we have to modify with some other material to see how this can be, that early age strength also can be achieved. So these are some of the research which is going on, and we are parallelly doing other tests also for confirming the durability of both the recycled fine as well as recycled coarse aggregate. Then now let me move on to the next another industrial byproducts what we are using for our research. We at ACRC we have done a good amount of research with fly ash, and we have a building which uses a 40% of fly ash. It has been constructed in 1970s itself. And as I mentioned, we have huge resources for coal-based power stations we have. So just because of that, we have more amount of fly ash generated. Nowadays, understanding the importance or benefits of fly ash in using cement. As I mentioned in the earlier slide, cement industries are the major contributors for CO2 emission. So if we are able to reduce the cement consumption in concrete, then we are contributing towards the circular economy for net zero emission. So what happens when we are using there, we are getting the dual advantage when we are using fly ash in cement. One is cement consumption is getting reduced. That depends upon what amount of fly ash we are using it. The code suggests that our Indian code suggests that we can go up to 35% of replacement. So we have nowadays in market, ordinary Portland cement is very less used now. and we are moving towards the Portland Pozzolana cement. So for most of the construction, major construction also, we are promoting Portland Pozzolana cement because the durability, not only the fly ash is reducing the cement consumption, and also it is having other benefits which provides good durability to the concrete. So because of that reason, we are moving towards fly ash. So now for 30-40 years, research has happened with fly ash, thanks to fly ash mission, all those things. So now we got the acceptance for fly ash as a replacement for cement. But if we see the thermal power stations apart from the fly ash, nowadays, which is having a huge demand from the cement industry, it is having other types of ash also, like store the ash which was stored for so many years, and pond ash, all those things, it is having a less value, and there is no takers for those ash, and this is still lying, and this also has to be addressed. So now coming to the benefits of fly ash, it is because it is having a spherical particles. Due to that, it improves workability and permeability. The size of the particles, it provides good permeability to the concrete. And when we go for a mass concreting, what happens is when we add water to cement, it is an exothermic reaction and it generates huge amount of heat. So when we go for mass concreting, then in that case, the incorporation or replacement of fly ash in that cement, it helps in reducing the heat of hydration. So the many things can be avoided, like the thermal shrinkage, cracks, everything can be avoided by using fly ash as an ingredient. So then, as I mentioned, the replacement level code has mentioned up to 35%, but nowadays there are so many research, and at CSIR-SERC also we have research to see whether if we go beyond 35%, what is happening, and how, if strength is reducing, how that can be compensated. So we want to use beyond 35% of fly ash. So that kind of studies also we have attempted. And when fly ash is used, it is having different roles. It is as I mentioned, it is spherical in nature. The particles are spherical in nature. So it has dilution effect, filler effect, lubricating effect. And when we add fly ash, the physical and chemical properties, so the inherent properties. So whenever we use some new material, either it is a virgin material or industrial byproducts, there are two properties which is affecting the strength and durability, or any other properties. One is the inherent property, like its shape, size, composition, etc. When it comes to external factors like the type of curing, the method of curing, and other external factors, the temperature, water to binder ratio, all those things. So when we use any new material, we have to give attention for this. The basic characterization studies we have to do to understand the physical and chemical properties of the material. Then the material can be used appropriately. The optimum level of replacement level can be judged based on the inherent properties of the material. And this is just to show that these are some of the tools we can use for identifying what is happening when we are using fly ash at different replacement levels. So this is when we are doing cement hydration. Here, this portion, it refers to the formation of calcium hydroxide. Because when we are talking about the strength, the strength for the concrete is promoted by the formation of calcium silicate hydrate. So when the calcium hydroxide formed, which reacts with the silicate to form calcium silicate hydrate. So depending upon how much of calcium hydroxide, this is the intermediate product which formed. Based on that, the strength can be increased. So here it shows that when we are going for high replacement levels, it is affecting the calcium hydroxide formation. Similarly, here what we have done, when we are going for high volume replacement, so if we see 20% replacement, and when we are adding this CF is a chemical admixtures we have added, that is calcium formate. So how it is altering the improvement in the formation of calcium hydroxide. And this is just to show, I have given very less results here just to show that how this replacement level when cement is used and when cement is slowly replaced from low replacement level to higher replacement level, how it is affecting the cement hydration as well as the strength properties. So we have carried out the elaborate test by using different type of chemical admixture and some waste like eggshell powder and lime sludge from paper industry. All those things are used as a calcium source when we are going for high level replacement of fly ash. This type of studies we have carried out. So those who are interested and they wanted to know more about that kind of studies, they can I have given the list of papers what we have published. You can refer to that in detail. Here this is just to show that this how it is affecting the strength when we are going from 0 replacement to 80% replacement. So here from different days, it is like when we are using fly ash, we have to see how early age strength is affected, and we have to go beyond the 28 days because it is pozzolanic in nature. So we can expect, unlike ordinary Portland cement, when we are incorporating fly ash, we can expect the strength improvement even beyond 28 days. So generally we do, because the first day, though this code standards are suggesting to go for 137 days strength, but generally we are very concerned about 28 days compressive strength. But here when we are using fly ash, we have to see how the early age strength is affected and how it is getting improved even beyond the 28 days. And these are some of the literature wherein we have studied how the fresh properties are affected, because the rheological property, if we want to develop self-compacting concrete, because self-compacting concrete has the advantage that it can even penetrate through the congested reinforcement. We don't want any mechanical vibrator for vibrating such kind of concrete. So when we want to develop such kind of self-compacting concrete, then the incorporation of fly ash, it is having a very good it provides flowability for the concrete, and we can easily get the self-compactability. So it is the rheological behavior we have studied. And as I mentioned, it is affecting the early age strength. So we have studied the early age strength and how that early age strength, the low early age strength can be improved. And we have used a different kind of admixtures, and also we have seen how the fly ash is mitigating the shrinkage. So there are different types of studies we have studied for this fly ash cement and fly ash concrete. And it is recommended that we can use good amount of replacement, like beyond 40%. Also we can go for it gives both environmental friendly concrete, and also it is having the technical benefits such as it improves the durability of the concrete. Then another type of concrete what we have developed, again it is how I can relate this to circular economy. This electrically conductive concrete has many applications, like it can be used for self-sensing, electromagnetic interference shielding, anti-static flooring, de-icing the pavements, cathodic protection, all those things. Generally, this electrically conductive conductivity to the concrete is not conductive in nature. It is generally having the resistance of 10 to the power 6 to 10 to the power 9 ohm centimeter. By incorporating some conductive materials, we can impart electrical conductivity to the concrete. By incorporating some conductive materials, we can bring down the resistivity to 10 to 10 to the power 5 ohm centimeter. When we get that kind of resistivity, then we call it as electrically conductive concrete. So generally, how this electrically conductive concrete is made by using carbon nanofibers, nanotubes, graphite powder, steel fibers, all those things. In this particular project, what we have done, whether some industrial byproducts can be utilized for developing electrically conductive concrete. So as I mentioned, whenever we want to do some use new material, we have to characterize, understand the material first and what is the composition, physical, chemical properties, everything. Then based on that, we can identify material which is used for particular function and application. So here in this case, our aim is to get the conductivity. So when high carbon content materials are available, because as I mentioned, in the conventional materials, the carbon fibers, nanofibers are providing conductivity to the material. So we have to see such kind of byproducts which is having the conductivity. So what we have done, this copper slag and steel slag, it is having a good amount of Fe2O3 content. So first we made some trials to see whether by incorporating this slag, whether it is improving the conductivity. So it was improving the conductivity. So then carbon black, again it is an industrial byproduct from petroleum industry, and bagasse ash, which is having a high carbon content. So this depends upon how the combustion procedure has happened. So rice gas, bagasse ash, there are so many biomass ash we have, so which is having high carbon content. This can be utilized for bringing the new function to the concrete. So this studies we have carried out, and for developing this special concrete, as I mentioned, these are the two criteria we have fixed: when presence of unburnt carbon content and presence of iron oxide. These two helps for improving the conductivity. So we have taken many industrial byproducts and we have tested the unburnt carbon content. This can be tested by using loss on ignition, and presence of iron oxide Fe2O3 content by chemical composition. So based on this, if these are different materials we have chosen, and we have carried out element oxide test for finding out the element oxides. So here Fe2O3 content are high in many of the things. If you see the copper slag, it is having around 60%. So it was actually providing the good electrical conductivity. So these are some of the test setup we have made for measuring the electrical conductivity. And this is just to see when we are adding conductive material, how it improves the conductivity. Means it is measured in terms of resistivity. When resistivity is getting decreased, the conductivity is getting increased. So if you see the scale here, it is 24,000 scale, 24,000 scale, here 6,000, and this is 8,000. So it shows that the electrical resistivity is reduced by 1 order when we are using copper slag. So for developing this kind of special concrete, this copper slag is good ingredient. So based on that, we have used this copper slag as a fine aggregate in this particular type of concrete. And this is again, it shows that when we use 3 different types of aggregates, this is having the this is a copper slag which is having the low electrical resistivity. And this shows that how electrical resistivity of mortar cubes and with and without conductive particle. Here how water binder ratio, how it is influencing the resistivity, and at various ages from 0 to 270 days. And here how the cement content, when we are replacing with bagash ash, how the cement content is influencing the electrical resistivity. And this is 2 different types of slag. We have used copper slag and steel slag. So Fe2O3 content is in that iron oxide content is in different forms. It is providing resistivity. So this knowledge and all we can receive by characterizing the material. And this is when we are bringing special functions to the material, means when we want to develop a new concrete, always the concrete has to be used in the construction. So it has to, by adding some different type of material, it should not affect the strength of the material. So the minimum strength has to be maintained, or like for a structural concrete, the code specifies that M20, that 20 megapascal strength of the concrete needs to be achieved. So this should not be compromised. When we are using some industrial byproducts for providing some special functions to the concrete, the strength cannot be compromised. So we have to see that whether it is providing what the functions we intended for, and also we have to check it is not affecting or compromising the strength. So this test and all we have carried out for this special type of concrete. So this also we have published. If you want more details about this type of concrete, you can go and refer our literature. Then I'll move on to the next type of concrete. This how it is contributing towards circular economy. There are 2 ways it is contributing for circular economy. One is this material, textile reinforced concrete. It is having a textile as a reinforcement. There is no steel required for this kind of concrete. This textile are non-corrosive in nature, and we can make very thin sections of out of this textile reinforced concrete. Here the ingredient for the textile reinforced concrete is, here it doesn't have a coarse aggregate. So we can make even from 10 mm thickness. This textile reinforced concrete can be made as 10 mm thickness without compromising the strength. So this is contributing towards circular economy by the way of minimizing the material which is needed. One thing. Another thing is it is non-corrosive in nature. So the life of this kind of concrete, it can be extended, or the durability is high. So these are some of the TRC application. The first one figure is first and second are from our lab, and these 3 are from the internet. And just to show that we can make a thin structure out of it, and what are the things we can make out of this textile reinforced concrete. We made like wall panel, door panels, all those things out of this textile reinforced concrete. So as I mentioned, it is having it doesn't have a coarse aggregate. It is having a fine grained material, and it needs a different type of proportion. Whenever we go for, or whenever we develop a new type of concrete, the basic ingredients may be same. Sometimes we need to add some new material for bringing some new functions, as I mentioned in the earlier type of concrete, electrically conductive concrete. Sometimes just by proportioning the conventional materials in a different way, for like self-compacting concrete, It can be made without adding any new material, but here the fine and coarse aggregate will be less. The paste content will be very high for providing the flowability to the concrete. So like that, for each and every type of, we have to keep it in mind that when we are going for a new type of concrete, we should change the proportion accordingly. So here in this case, there is no coarse aggregate, and maximum size of the aggregate should not be greater than 2 mm, because we have to maintain the integrity between the fiber which is placed, the textile fiber which is placed along with the matrix. So these are all some of the different types of textile fibers available in market, like alkali resistant, basalt fiber, carbon fiber, aramid fiber, etc. And this is the mixed proportion and how this can be laid. This is manually, and we have a machine also automated to make the textile reinforced concrete. So this can be placed in layers. This is a composition given here for this particular thing. Earlier it was using only the quartz powder or quartz sand, but nowadays because it was very costly previously. Now it has been reduced. Now because of we have replaced that quartz powder and sand with the river sand. So it is like the number of layer depending upon the requirement. What tensile property we have, what flexural behavior we are expecting from this particular type of textile reinforcement. We can increase the thickness from 10 mm to 30 mm, 40 mm, whatever it is. And depending upon the requirement, we can keep one or more layers of the textile reinforcement. And here, this we have carried out studies to see when it is subjected to high temperature, how it is disintegrating, because it is having a layer of fibers. So this shows that after around 600 degree, when it is subjected to 600 degree only, the fibers are getting disintegrated. And this is other studies to show that how this disintegration happens when under scanning electron microscopy, how that fiber bundles are affected when it is subjected to high temperature, and how this interfacial transition zone is getting affected when it is subjected to high temperature. So these are some of the studies we have carried out, and this we have seen how that different environments. That this is a tensile reinforcement cured in different pH solutions, and pH solutions were tested for any dissolved materials, whether that has been leached out of the textile reinforced concrete. And this we have carried out the deflection test with the various thickness of the specimen. This is subjected to different exposure conditions, like different pH conditions, to see with acidic condition and alkaline condition how, because the matrix is rich. If you see the composition of textile reinforced, the composition is very rich, so it is not supposed to affect the fibers with the different exposure conditions. So we have subjected to acidic as well as alkaline condition. So we have tested for a different thickness. It was showing that it was having a good resistance to water permeability as well as the alkaline resistant, and this also we have published. So if you want more details, you can go and refer our literature on TRC. And another thing is steel slag concrete. So what we have done here, there's industry came to us because steel slag, it is not like ground granulated blast furnace slag. This electric induction or furnace slag are not used in by the cement industry. So they have come to us to ask whether this, because they have a huge pile of slag stored in their industry, they wanted to convert that slag as some useful material. So this way we have contributed towards the circular economy for converting this slag into the fine aggregate. So this is the boulders, slag boulders, and this has been crushed and sieved under 2.36 mm sieve. And this fine aggregate, this is called a slag fine aggregate after crushing. And this slag fine aggregate is used instead of conventional river sand. So we have compared with when river sand is used, how it is behaving, and when slag sand is used, how it was behaving. So it is like three different sand we have taken. One is M sand, one is normal sand, another is slag sand for both OPC and PPC. So we have to see that whenever we use some materials, we have to see, because the compatibility between, as I mentioned, this Portland Pozzolana cement is having some pozzolanic material, it behaves differently. So we have to understand that how it is behaving for different types of cement. So for that, we have conducted some study for different types of aggregates with different types of cement. And what we have observed from this study is both the strength as well as durability point of view. When we are using slag sand as a replacement for river sand, for 100% replacement for river sand, it is not affecting the strength or durability properties. So we have suggested this can be used as a good alternative for river sand. And this also, it is available in literature. If you want more details, you can refer this paper. Then coming to another type of concrete, it is a pervious concrete. So here it is made of no fines, like less amount of sand or no sand. So it is made with coarse aggregate and cement paste. So the advantage of this concrete is it is porous in nature. So it promotes the groundwater recharge. So if you pour water, it will come out of the other side. So it is having a good amount of voids. So as I mentioned, this is a type of concrete. So we need a different type of proportion for this type of concrete. And I mentioned here that it doesn't need any sand or very less amount of sand. So whatever we have made is without any sand. And here here this type of concrete, the importance is here the void content. So it is designed generally for a strength purpose. We used to fix a strength like 20 megapascal, 30 megapascal, and we design the mix. Whereas here we have to see how much voids we need. Based on that, we have to design the mix. So this is how we have it looks like. And this concrete is used for side walkways because it is having a voids. We cannot expect more strength. So if you see here, the highest is around 9 megapascal. So this can be suggested, or this can be recommended only for very low traffic or side walkways, such kind of thing. But what we have done, this because it is porous in nature, we felt that these are some of the architectural concrete, like green concrete, wherein vegetations are grown vertically. So what we have thought, because it is having voids, that voids can be filled with some growing medium like compost, and vegetations can be grown, and this can be used for, because this type of vertical green gardening is having advantage, like when it is kept in outdoor or indoor, it purifies air, and it provides the temperature has been reduced, so noise sound insulation. So there are so many advantages of keeping this kind of vegetation on the vertical wall. So why not we can try that. So for that we have tried, like this porous concrete is filled with compost, and vegetation is grown over that. And this is how the vertical slab is made with this pervious concrete. And this also we have published. If you want more details about this pervious concrete, you can refer to this. So these are all some of the types of concrete I would like to discuss here on in this lecture. And now we can, these are all different types of materials. made by using how we can relate to circular economies. As I mentioned here, most of the things in almost all the different types of concrete, we have used industrial byproducts as a ingredient. And when we move on to the, there are some other methods by which we can achieve circular economy, like modular construction, high value recycling and reuse, sharing space. Now this is now sharing space or getting familiar, like we have Workafella. So same space, instead of each and every company is buying their own space, the space is commonly built, and whenever they need on a sharing basis for weekly rental or daily rental or monthly rental, that can be. So the number of construction of buildings can be reduced by sharing space. So this and 3D printing, this provides a faster construction. So by this different ways we can contribute towards circular economy. And this is just to show that how modular, what are the advantages of modular construction, like faster construction, minimum site work, uniform finish, building components, almost all building components can be made. And nowadays we have a technology in such a way that we have the component level, and this can be dismantled and this can be fixed in somewhere else. So when we want a temporary structure, it is not necessary we have to construct and leave it or demolish there. And we can, now technologies are available, when the purpose is over, that can be dismantled and this can be used in some other place where it is needed. So those kind of technologies are available now at component level and structural level. So this is one live example I just want to show for that circular economy. This is one building in New Delhi. They wanted to demolish it first. Then they thought that how this can be converted. Instead of demolishing, this can be converted and converted by adapting new technologies like design for disassembly, adaptability, remanufacturing, whatever I told you. So they have converted this building into a new building instead of demolishing. Now the life of this building has been extended. So with this, I'll have few more examples. I think I have some more time. I can show these examples, how the sustainable buildings. Initially, I mentioned that this structural engineer or construction, that construction industry, it is contributing towards the environmental degradation. At the same time, this construction people, this concrete industry, otherwise the structural engineers or material scientists, they are also contributing for the innovations to combat all these things. So so many innovation happened in this area to bring sustainability to the buildings. As I mentioned earlier also, like vertical green spacing, which helps in bringing sustainability to the buildings. Like that, there are so many standing examples. So I would like to list few here. One is the Sun Moon Mansion in China. It is a fan roof which is having 5,000 solar panels. And in this buildings, they have used more than 30 advanced technologies like grid connected power generation, for photovoltaic cells, photoelectricity, sunshades, northern grilling sunshades, like many technologies they have used in this particular building. And they have achieved the energy efficiency of around 88%. So using the solar panels throughout the building, they have used around 5,000 solar panels. They were able to save around 2.5 tons of standard coal, 6.6 million kilowatt hour of electricity, and more than 8.6 tons in toxic emissions. And this is in India. We have another standing example for such sustainable building. It is Switzerland One Earth in India. This campus, it is powered by renewable energy, including hybrid wind turbines, solar panels, and photovoltaic cells, and it conserves 35% of their operating cost. And it got this platinum LEED and Terry Griha 5-star certification, with 8% of its annual energy generated on site through photovoltaic panels and windmills, with a total incremental cost of about 11%. So not only, these are only some examples, and throughout India, and we are moving towards renewable energy. So we are able to, and after some time, as we are now till today, we are having good amount of coal resources. We are power generation happening with the coal power stations, but we are slowly moving towards renewable energy also. So this renewable energy, even for small structures like this photovoltaic panels are used in many places for even for small projects. So in this project, they have used a good amount, and they were able to declare it as a zero energy project. And this is by way of designing. So by reducing the amount of energy, by the way it was designed, the daylight and the natural ventilation is taken care of. So by that, they were able to conserve good amount of energy, and 100% rainwater is harvested. So these are some of the technologies we can adapt to bring circular economy in the construction. And this is another example. This is like a living museum, and 4,000 square feet lagoon fed by roof runoff. It contains native fish and turtles and is bordered by an FSC certified oak boardwalk. And here they have managed 10-year storm through vegetation-based system, including green roofs, gardens, and biowheels. Annually, approximately 500,000 gallons of rooftop runoff offset the conservatory irrigation demand. So it is like no potable water used for irrigation since landscape establishment period. So this was achievement they have done by just by maintaining some new practices and maintenance practices apart from construction. As I mentioned, whatever it is, not only during the construction and after construction and during the maintenance period also, it is contributing for the energy and emissions. So that can be avoided by proper planning during construction and proper maintenance, and fixing few technologies which can save energy and water. And with this, I'll conclude this lecture. So circular economy is about like CO2. It addresses, when it comes to built environment, it addresses CO2 emission reduction and material cost reduction, increased use of construction and demolition waste, because this construction and demolition waste is a huge amount of waste. When we see the development of infrastructure in any country, especially developing countries like India, so the amount of waste generated by construction and demolition is huge. So that needs to be addressed. And the pathetic situation in India is we are only using 1% of construction and demolition waste. So when this level of utilization is increased, then we can save good amount of natural resources. So by adapting a circular economical practices, technologies, we can save our planet, we can save our natural resources, and we can keep some resources for our future generations. With this, I would like to conclude, and thank you all.
Thanks for your wonderful presentation, ma'am.
Thank you. Thank you. Any questions?
I request participant, ma'am, they are asking comprehensive strength available for the bamboo fiber,
Okay.
concrete instead of steel.
Okay.
Any data on comprehensive strength available for the bamboo fiber reinforcement, concrete instead of steel?
Sir, actually, we didn't use I didn't do any research on bamboo, but our sister laboratory, CBRI.
Madam, very good presentation.
Yeah.
Hello.
Thank you. Thank you. Thank you.
Hello, madam.
Yeah.
Hello.
Yeah, please tell me.
Thank you, madam. I have a small doubt, madam.
Yeah.
Very good presentation. I am also working on the same area on special concretes only.
Okay, sir. You are from which Indian institute, sir, please?
I'm from NICMAR, madam.
Okay, okay.
Yes,
sir.
Research, and you are professor and register. And
Yes,
I am
sir.
also working the same field.
Okay,
and I hope
sir.
Bhaskar is your colleague, madam.
Okay, 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 sir.
Bhaskar you may be knowing.
Yeah.
Bhaskar is my friend.
Okay, sir. Okay, sir.
And is my senior, Bhaskar.
Okay, sir. Please tell me, sir.
Madam, I have a small doubt, madam.
Yes,
This
sir.
was a rock painting, that's why I joined this course. Madam,
Okay.
can we use, how much percentage of recycled aggregate can we use in concrete, madam?
Sir, recycled coarse aggregate or fine aggregate?
Coarse aggregate.
Okay. Coarse aggregate, actually, my colleague is working on that. What he has replaced from 20% to 100%, and have observed that when we go for 100% replacement, it is reducing by around 30-40% strength. Like he got 40 megapascal when it is 100% conventional aggregate. It comes to 29 megapascal with 100% recycled aggregate.
Because
So,
it consists of filament.
it is, sir, the fact we have to agree is when we are using recycled aggregate, it is reducing. But we have to see what is the target strength, our target strength. So accordingly, we can modify the replacement level. If you want 30 megapascal, even this 100% is also giving around 29 megapascal.
But we cannot go for high strength, we cannot use it.
High strength, sir, this is the research what we have started very recently. But if you want high strength, we can modify the cement, sir. Cement with some silica fume. So,
yeah, that too can do it, madam.
Yeah, proportion.
Recycled aggregate. Madam, is there any code is there? Madam, code book is there?
IS 383 is suggesting
for coarse aggregate. IS 383 1970 for coarse aggregate.
IS for recycled aggregate, I am telling, sir. For the basic properties of recycled aggregate, IS 383. But recycled coarse incorporating 100% recycled coarse aggregate, no code is suggesting, sir. We have to do research and we have to bring acceptance, then we have to bring it into the code. So that takes some time.
Because I am also the BIS member also.
Okay.
That's
Sir,
why
then we have to work together and we have to modify the code.
Yes, madam. That is the main purpose of joining this course, madam.
Okay.
Waste to wealth invention. And that's why Navin sir also kind enough to give to bring you people like and making this platform highly useful and highly effective.
Yeah.
Thank you, madam. Thank you, madam.
Thank you, sir. Thank you.
Sorry for inconvenience.
Any other query?
Madam, can you hear me? This is
yes.
Dr. Jayapal from NIT Jamshedpur.
Yes, sir.
Ma'am, I am basically a geotechnical engineer.
Okay,
and
sir.
whatever slides you have been discussing related to fly ash, do they belong to high calcium or low calcium fly ash, ma'am?
It is class F fly ash, sir. Low calcium.
That means low calcium fly ash.
Yes, sir.
Okay. Ma'am, actually, I'm teaching a subject called as sustainability, in which I'm teaching a bit of utilization of bamboo as a reinforcement in concrete.
Okay.
is there any data that is available or design codal provision that is available that I can use it for designing a column or maybe one-way slab or a two-way slab, something equivalent, using only bamboo reinforcement, not conventional reinforcement?
Sir, actually, in CRC, we didn't do any bamboo research. But,
Okay.
but in our sister laboratory, CBRI, they are working on bamboo research. So, sir,
Okay.
and lots of literature available. You can connect to some CBRI people, sir. You can search in our CSIR CBRI. There
Okay.
you can get some good connection. They can help you because they have done some research. At SCRC, we didn't do on, I have just done some literature survey. So with that, I cannot answer your question, sir. We didn't do
Okay,
any
ma'am.
research.
Okay, ma'am. Ma'am, I have one more question. It's like,
Yes,
what
sir.
kind of geofabric or synthetic fabrics do you generally prefer for reinforcing concrete?
Sir, we are using, because carbon fiber is very good, but it is bit costly. So we
Okay.
are going for aramid or glass fiber.
Okay, okay, okay. ma'am.
Like for this textile reinforced concrete only you are asking, no, sir?
Yes, 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 yes.
Yes,
ma'am.
sir. These
Is
two
there-
are we are using because of the cost aspect. When carbon fiber is also good, but cost is bit high.
Okay, ma'am. So is it possible to make as thin elements something equivalent to 10 millimeter, ma'am?
Yes, sir. Yes, sir. We have made.
Okay. Okay, ma'am. These are the questions. And thank
Yeah.
you. It was a very nice lecture.
Thank you, sir. Thank you.
Thank you, ma'am.
Hello, madam.
Yes, sir.
I have just one question. You are talking about recycled aggregates. So, when we are using the recycled aggregates in the new concrete, how much the strength of the new mix is affected by that?
Sir, actually, this research is going on. We didn't come to any conclusion, right, that what percentage replacement we can go. The basic research, what I have done so far, that too by using recycled fine aggregate, as strength point of view, it is not affecting much. At 28 days, we are able to get the strength which is equivalent to the conventional aggregator. But when it comes to the concrete, we have to do lots of study to confirm that 100% replacement is not affecting. So I have done only so far up to the mortar level.
Oh, okay, madam. And another thing, you have said that you are using till now you have used the recycled fine aggregates. Ma'am, how are you processing that? How are you extracting that from the used materials?
Sir, this actually we have a processing unit in Chennai, recycling unit for recycling aggregates. So in my slide, I have shown like this heap of sand. It is like they have made it like in the processing unit, they are crushing and keeping aggregates of different sizes. In that one size is this fine aggregate. This is the.
Oh, yeah. Okay, madam.
Yeah, this is
so
the
madam,
how it is processed.
So madam, when you are extracting this, when the processing is going on, I think there is some little bit maybe the difference between the actual fine aggregate that is naturally available with that.
Yes, sir. Yes, sir, it is, sir. That's what. This is not equivalent to the aggregator, original aggregator. It is a combination of so many. It is having so many composition.
Which kind of test you perform on that?
Pardon?
Ma'am, I am asking which kind of test you perform on that. In this,
For characterization. Hello? Hello.
yes, madam, your voice was not audible for some time.
Now is it audible?
Yeah,
Now
ma'am.
is
Now
it
it is audible.
audible?
I am asking which kind of. Yes, madam. It is now audible. I am asking that which are the tests that you perform for this kind of recycled fine aggregate.
Sir, am I audible, sir?
Yeah, it is audible. Please go ahead.
Yeah, please.
Ma'am, am I audible, madam?
Yeah, now audible. Tell me.
Ma'am, my question was which are the tests that you perform for this fine aggregate?
Okay. See, for characterization, physical properties, we have carried out like specific gravity, water absorption, bulk density.
Okay.
So all
Okay.
the basic tests we have carried out to ensure the difference between conventional aggregate and this fine aggregate. Then later, when we are using it as a replacement for conventional aggregate, the conventional test like compressive strength, and for durability, we have conducted water absorption, sorptivity, RCPT.
Acidity test you conduct, madam?
Acidity means for the fine aggregator after casting.
After casting. Okay. Okay, madam. Thank you, madam. Thank you.
Any other queries?
Okay, ma'am. Thank you.
Thank you so much. Thank you for the opportunity.
Yeah, it was a wonderful presentation, ma'am. Thanks a lot. Okay, Abhijit, you can stop recording. We can start the session after 10 minutes.
Okay, sir. Okay.
Okay, sir.
Ma'am, you can leave now.
Yeah, thank you.